Okay, so jumping into 7.2 part 3, this will be the last part here. This one isn't super important as far as the homeworks go, but it is important for definitions and how the Laplace transformation works. So there's going to be a lot of writing and typing in this one. So first thing I want to say is that there are examples of functions that do not have a Laplace transformation. Just as a quick example, the function 1 over t. You cannot find a Laplace transformation for this. It just doesn't exist. So we need to figure out when do we have functions that do have a transformation and when do we have functions that do not have a transformation. So let's look at some definitions. A function f of t on some interval a to b has what's called a, I'll underline it here. Oh, it did not underline. Why not? Underline. A jump discontinuity. Okay, so a jump discontinuity is defined like this. So it's at a location which we'll just call t naught. This t naught has to be somewhere in between a and b if f of t is discontinuous at that value t naught. But the one-sided limits, so let me write these out. This will be the limit. I got to do the special limit stuff, sorry. All right, so this is going to be the limits from the left and to the right. So as t approaches t naught from the left-hand side, of the function f of t, and then the other limit, same thing. So this would be the limit, but this time approaching it from the right-hand side. So as t approaches t naught from the right of f of t, if both of these exists. Okay, so just to go back and read through the definition here, we have a jump discontinuity if it's discontinuous at that value, but the left-hand values and the right-hand values of the limits exist. Just to try to explain exactly what this is, okay, I had to get a little drawing thing here. So to explain what this means is that if you do have some kind of graph, a jump discontinuity is when it does like a jump, right? So maybe it has an open value here, and then it jumps up here and then continues on this way. So this is a jump discontinuity. It's discontinuous at this point, but the limit from the left and the limit from the right exists. What is not a jump discontinuity is where you have an asymptote. So if the function approaches the asymptote to infinity that way, maybe a negative infinity that way, this is a discontinuity, but it is not a jump discontinuity. A jump discontinuity has to be something like this. Okay, cool. How do I get rid of this? Go away. Hide cursor. No. I did it. I figured it out. Okay. Moving on to another definition here. So the next definition we need to talk about, this one's a little bit longer. A function f of t is what's called piecewise continuous on a finite interval a to b if f of t is continuous at every point in that interval a to b except possibly for a finite number of points at which f of t has a jump discontinuity. Okay, so we call something piecewise continuous if it's continuous everywhere except you are allowed to have a finite number of these jump discontinuities. So as long as you have a jump discontinuity, we still call it piecewise continuous. Okay. Last thing we want to write out as a definition here, and this is the most important one. This is the definition we're going to be using moving forward. A function f of t is said to be of exponential order, alpha. Find my little alpha symbol here. Alpha. If there exists a positive constants t and m such that, and then we have this inequality down here. So the absolute value of f of t is less than or equal to m e to this alpha capital T. Oops. Oh, sorry, not capital T, little t, for which t has to be greater than or equal to capital T. Okay. So I know this may be kind of too new and weird, but this is important for these Laplace transformations. A function f of t is said to be of exponential order alpha if there exists a positive constants t and m such that the absolute value of f is less than or equal to m e to the alpha t for some starting location. Let me get my drawings. Okay, so if we have our x and y axis here, basically what this is saying is that as long as the function f of t is below the exponential function m e to the at. So exponential functions, remember, they just do something like this, right? They blow up really, really quickly. It doesn't really matter what f is doing as long as f is bounded from above by this exponential function. So maybe it's doing something weird like this. Or remember, it can have these jump discontinuities to it as well. Whatever. As long as the f is below this exponential function, and it doesn't have to be forever, like maybe f is doing something weird here, as long as at some value capital T, it's eventually below it. We call it of exponential order alpha. Okay, let me get rid of this stuff and I'll come back. All right, so just a quick example. Let's look at the function f of t is e to the 5t sine of 2t. Okay, e to the 5t sine of 2t, the e to the 5t is going to be the dominating term here. Sine of 2t, remember that sines and cosines always kind of alternate or go back and forth between -1 and +1. So this isn't going to do anything as far as it blowing up to infinity. This is just going to make it go back and forth like a sine wave, basically. But a sine wave restricted by this e to the 5t. So it is going to be a sine wave that eventually blows up and gets bigger and bigger and bigger. But it's still bounded by this e to the 5t. So what we would say is that this function f of t is of exponential order 5. Exponential order 5 because this is always bounded by the overarching function e to the 5t. Okay, and one last thing we're going to write down, and this is the whole point of all of these definitions. So here's a quick theorem. This is the existence of the transform theorem. Okay, and it's real quick. If f of t is piecewise continuous on some interval where this interval has to go from 0 to infinity, and of exponential order alpha, then the Laplace transformation of this f of t of of s exists as long as your s is greater than alpha. Okay, so basically what this is saying, right, is that we know the function is going to exist as long as it is piecewise continuous from 0 to infinity and it is bounded by an exponential function of alpha t. And as long as it is bounded by this exponential function alpha of t, that alpha is going to be the restriction for my value s. Okay, so we're going to be moving on to section 3. Section 3 is going to be looking more at the properties and kind of the whole point of why we're even talking about these Laplace transformations.